So, hello everyone, I am glad to see you back on my channel, and today we continue to solve and prepare ourselves for practical tasks on the interviews for the most popular companies, fun companies in the world. And today we will check the new exercise, which is called minimum stack of medium level. And let's continue and try to understand the algorithm first. And I think that the main idea of this task is that we need to implement a stack, which, in addition to usual push, pop, and top operations, and here I want to make a small explanation. So first of all, if you are not familiar with stack is a data structure which is working by principle first in, actually last in, first out. So the last element which we'll put in our stack will be the first element which we will get. And we will need to implement such methods like push. This method adds an element on the top of our stack. Pop is a method which will return the top element of the stack and also will delete this. And top is a method which will return the last element from our stack without deleting it. And also we will need to implement another method which will return the minimum element of the current stack. And also one very important condition is that we will this method, which will return the minimum value, should work on time complexity 01. And the problem here is that if we simply store one regular stack, so let's imagine we will create our implementation of this data structure, which we will call our stack or something like that. And if for the implementation we will use just a stack, we'll see it a little bit later, then to find the minimum elements we would need to go through all the elements every time. And then the complexity would be 01, and that actually doesn't satisfy our requirements. Yeah, so let's imagine we, for our implementation of our stack, would use a stack. Yeah, and in order to find the minimum value, we would go through each element of this stack. Yeah, and again the complexity would be on n. But we need 01, so we need just one operation in order to find the minimum value. So to solve this problem, we set up two stacks instead of one. So the main stack is where we push all elements as usual, and an auxiliary minimum stack. So we will have two stacks. One simple stack where we'll push our elements, and minimum stack where we will store minimum values, and which yeah, so that's the main idea here. And also another important thing to understand is that the top of the minimum stack always holds the minimum element for the current state of the main stack. So let me show you an example, so how this algorithm is working. So let's imagine that initially we want to push an element in our stack, and we will have inside our implementation two stacks again, where we will push just elements. It will be a simple stack, and stack which will hold minimum values. So let's first push the first element, which will be 1. And because we don't have enough values inside our stack, also the minimum value will be 1. Yeah, because we don't have another values with what we can compare. Then let's imagine that we push another element, let's say, let it be 2. And now we need to compare 2 with the minimum element which we have in our stack of minimum values. Yeah, because the previous minimum element was 1, and now we compare 2 with 1, and we can see that 1 is still the minimum element in case when we have in our stack 2 elements, 2 and 1. So here we push again 1. Now let's imagine that we add another element, let it be 3. And again, we need to compare 3 with the top element from our stack, which holds minimum values, and this is 1. So we compare 3 with 1, and we again can see that 1 is still the minimum element. So let's imagine that we have stack with 3 elements, 3 to 1, and the minimum element from this 3 is 1. So we push again 1 here. And now let's imagine that we add 0. And now we again need to compare this new value which we have pushed inside our stack with the minimum top element from the stack which holds minimum values. And now the minimum element will be 0, yeah, because 0 is less than 1. And let's imagine again that we add another element, it will be again 1. We compare it with 0, so 0 is still less than 1, so the minimum value will be 0. So for the stack which contains these elements, where the top one is 1, then 0, 3 to 1, the minimum element is 0. And now you may ask me, so is it possible a situation that we delete the minimum element from this stack, but it remains so actually no, is it possible if we delete the minimum value from this stack which holds minimum values, but it remains here in our simple stack? And the answer will be that no, it's not possible. Actually, yeah, so it's not possible that in our stack we will have minimum value, but it will not be in the stack which holds minimum values. Why? So let's try to do this. Let's try to pop elements step by step. So let's imagine that we pop element from our custom implementation of the stack. It means that we will need to delete top element from our simple stack, and also we will need to delete this top element from our stack which holds minimum values. And now we will see that the minimum value from these values is still 0, and we have this value in the top of our stack which holds these elements, minimum values. Now let's try to pop again 0, and here also we need to delete. And now we can see that our stack, simple stack, holds these 3 elements, 3, 2, and 1, and the minimum element for these elements will remain 1, which is a top element from our stack which holds minimum elements. So everything is correct. Yeah, so here is the main idea. And now we can conclude three things. That first one is that when we push something, it means that we need to compare the new element with the current top of the minimum stack and push the smallest of the 2 values onto the minimum stack. The second condition is that when we pop, we need to remove an element from the both stacks at the same time. So we will remove it from the simple stack, and also we will remove it in the same time from the stack which holds minimum values. And the last condition is that when we call method getMin, which will return us minimum value of our stack, we simply return the value at the top of the minimum stack without any calculations, since it's already prepared. So that's why we will have the complexity O1, because we just take the top element from stack which holds minimum values. So essentially we sacrifice extra memory because we need to create additional stack which will hold minimum values, but we get constant time for the minimum finding operation. So that's the idea. I hope it was clear. And now let's proceed and check the implementation of this algorithm. So, because we want to create our custom stack, we will need to create our class where we will implement methods, which was specified in the condition. And I have created a class which I called minstack. All right. Now the first thing which I want to do, I want to create two stacks which I will use for my custom implementation. So let's declare here two fields, two variables, the codinginterview, and we will call it stack. Here we will store in a simple way elements when we will push them, and also we will need to create another stack where we will store minimum values. And let's call it minstack. Again, you may notice that here we write the queue. Actually, in Java, this implementation can be used like a queue and also like a stack. So this is a stack. Yeah, so we can extract the top element from this data structure. And now let's create a constructor for this class. So let's do this. Minstack, where we will initialize our fields. Okay, perfect. And now let's start the implementation of our methods. So let's start first with method push. And like argument here, we will put an int value, which will be our value, which we want to push in our stack. Okay. Now, what we will need to do here. So first, we will need just to push this element inside our simple stack. So let's do this. We will use push method from for the queue implementation from array deque. So we will push this element. And now we also will need to push this. Probably we will need to push this element inside our min stack, but we will need to verify something. Yeah, so if this new element is less than the previous one, that means that we need to push it in our min stack. If not, then we will not do this and we will use the previous element. So let's check this logic. So first, let's validate if min stack is empty. Then let's add this element inside our min stack. You may ask why we are doing so, because if our min stack is empty, it means that this element which we want to push will be the first element not only in the min stack, but also in the simple stack, which means it's the first element. Yeah, and because we don't have any element with which we can to compare, we just added like a first element inside our min stack. But also we can have a situation that when we already have some elements with what we can start to compare. And for this, let's write here else. So if the stack is not empty, then we will push inside our min stack the minimum element between the value which we want to add and the top element from our min stack. So let's take the min element from the min stack, from the top of min stack, and let's compare it with a new element which we want to add. Okay, perfect. So that's the implementation for push method. Now we can continue and try to implement pop method. So let's declare this method. So what this method does, it takes the top element from our stack and delete this. So it means that we will need to perform pop operation for our simple stack, and also we will need to do so for our min stack. And again, we are not afraid that we will delete a minimum value from the minimum stack and it will remain in our simple stack, because it's impossible. If you didn't understand this logic, you can try to rewatch the previous example and try to understand the algorithm. But if everything is clear for you, let's proceed and try to implement our method, which is called getTop. So let's do this. GetTop. And this method should return us the top element from our stack without deleting this. So here it will be enough just to call pick method from our stack. Pick is a method which returns the top element from the stack without deleting this. And the last method which we want to implement is getMin. So let's do this. Public integer getMin. And this method should return us the minimum element and the time complexity should be 1. But we already have this stack which contains the minimum element, and this element is the top element from min stack. So we just can return the top element from the minimum stack. So we have implemented all methods, and this is the correct implementation. I hope all this is clear. If you have any questions, please write them in the comments. And now let's check the complexity. So The time complexity for our solution is O1 because we can extract the minimum value in constant time. And the space complexity is ON because we have created additional stack to hold minimum values. So that's the solution. That's how this algorithm is working. I hope that everything was clear, and we will see you in the next video. Bye.